Hello, I am Dr. Abhishek Joshi, and today I am going to discuss about the random processes. So this is the lecture dedicated to the random processes. So what is a random process? So if a random variable is defined for a time interval, so if we are defining the random variable for the time interval, for example TATB, so this time duration TATB is a function of time. So this xt, we are making it as a function of time, then we will call it as a random process. So random variable that is a function of time is a random process. So we are saying that the random variable that is a function of time is called random process, or it is known as a stochastic process. A random process is a collection of an infinite number of random variables. So we can have infinite number of random variables like x1, x2, x3, or y1, y2, y3, or x, y, z. Any variables we can take. So communication signals such as noise, typically random, and it varies with time. So this is the best example to consider a random variable in communication, or we can say digital communication. We will considering noise as a random variable or random process. To specify a random variable, we run a multiple trials of an experiment. From the outcome estimate the p of x. So what is this p of x? This we have discussed in our previous lecture as well. It is nothing but the cumulative distribution function. If we are using a small p, it will be probability density function. So it estimates the probability cumulative distribution function, that is a CDF. So similarly it will specify the random process xt, and we do the same thing for each time instant. So what is the best example to consider a random process? The best example is the temperature. So temperature is the best example to consider it as a random process. So the collection of all the possible waveform is known as ensemble. So we have different for random process, since we know that it's a collection of varying with time, and it's a collection of different waveforms. So the collection of different waveforms, and this is a function, for example we are considering a random variable x, and it is a function of time. Now this xt will have different waveforms, and it is varying with respect to time. Okay, so we will call the collection as ensemble. So collection of all the possible waveform of a random process is known as ensemble, and the waveforms, these waveforms 1, 2, the waveform 1, waveform 2 is known as the sample function. So these keywords are clear, that the collection of all the possible sample functions is known as ensemble. Okay, so this is a example. It is showing that this is a collection of different waveforms, and we have, for example, waveform 1, waveform 2, waveform 3, and waveform 4. So these 4 waveforms are forming one ensemble, and this is showing the example that the temperature of a city. So temperature of a city here is, we are considering it as a random process. Now the collection of all the possible waveforms is known as ensemble, and these are the sample function. So sample function 1, sample function 2, sample function 3, sample function 4. So these are the 4 sample function of an ensemble. So random process to represent the temperature of the city, this example we have considered as a random process. Now we can say that the output of the random binary generator, which is widely used in communication, will generate the data, digital data, and it is random in nature. So due to the randomness we are called, and it is the function of time. So with respect to time it is varying. So data is varying with respect to time. So this is the collection of all the possible waveform of random binary generator. It generates the bits randomly. So this collection is known as ensemble. So here we have considered only 4 possible waveforms. That is why it's written that ensemble with a finite number of sample function. So the distribution and the density function of the random process. Similarly, whatever we have discussed in the random variable, same is applicable for the random process. So the density function and the distribution function which we have described for the random variables are varying with respect to different time instants, because here we are sampled the time with the random variable. So we have mapped the time with the random variables, so that's why the functions are continue with this random variable. So what we are considering the case, we are considering n random variables like x1, x2, x3 up to xn generated by the amplitude at the time sample t1, t2, t3 up to tn, that represents the dependent on in general for the n samples. So how many samples we have taken? We have taken the n number of samples that is fully characterized by nth order of the joint probability density function. So here we are calling it as a joint probability density function because we have considered multiple random variables at different time instant, that is t1 up to tn. So we are calling the joint probability density function, and we will call, or we can find, the nth order joint cumulative distribution function. So these two important factors are there for a random process, and we will denote the joint distribution or the cumulative distribution function by capital F. Similarly, the joint probability density function, we are denoting it by small p, or we can use small f. So in some books you will find small f as for the joint density function or joint probability density function. In some books you will find the small p for joint probability density function. So we can write the distribution function as f of x, that is a function of x1, x2 up to xn at a different time instant t1, t2 up to tn. So this is nothing but it is a PDF of the, or you can say the probability for xt less than x1, probability that xt is less than, because we here is a function of time, xt is a function of time here, and it is less than x2, or we can write up to xtn less than equals to xn. So the joint PDF we can relate with the joint cumulative distribution function if we differentiate with respect to the variables. So if we are differentiating, because here we have n number of random variables, so we'll differentiate up to n, x1, x2 up to xn for different time interval t1, t2 up to tn. So we are differentiating del raised to power n. What is n here? N is the order of the function. So order of if n equals to 2, then it is v second order, n equals to 3, it is third order. So similarly it may have any integer value, n equals to 1, 2, 3, and we have the order. So del for n equals to 1, it is the first order, or we can call it as the lower order. Okay, and n is greater than 1 is known as the higher order. So higher order and lower order we can classify, and del raised to power n by del x1, del x2 up to del xn, and the cumulative distribution function. So we have to differentiate this cumulative distribution function for the variables x1, x2 up to xn. So it's a function, because we know that the cumulative distribution function is a function of the variables for x1, x2 up to xn for different time instant t1, t2 up to tn. So we can find the lower order PDF from a higher order PDF. If we know the higher order PDF, we can find the lower order PDF simply by integrating from minus infinite to infinite p of x for the variables x1 and x2 here for the time instant t1, t2, and we are integrating with respect to dx2. So we will get the lower order, that is for the first time interval, that is t1, that is x1, t1. Now how we can find the mean of a random process? So the mean of the random process xt, also called as the ensemble average. So here we are calling it as an ensemble average. We are not calling it as simply the average or the expectation. We are calling it as an ensemble because we know that the random process is a collection of different waveforms, and the collection of different waveforms is known as the ensemble. So here we are getting the ensemble average, that is the expectation of x of t, or we can write it is xt bar. And we know that according to the definition of expectation, it is nothing but integration from minus infinite to infinite x p of x x comma t dx, because we know that the probability density function pdf is the function of time, that is x t. So and here this is, we have to keep in mind that we are not integrating with respect to time, because here this function, that is a probability density function, is a function of the random variable, and here we are talking about the random process, we are not talking about the time varying function. So here we have to integrate with respect to the dx, not with dt. So we have to keep in mind that here the derivative should be for the random variable only. Now the variance, so we can find the variance of the random process by variance, that is sigma square del t, and this is equals to the expectation of xt minus mu of xt whole square, and this we have derived earlier also, that we can simply write it as expectation of x square t minus the expectation of x whole square, or we are denoting the expectation as mu here. So we can denote expectation as the mean or the mu of x. So both are the same thing. So here is a time varying function, so we can write as t as well. Now the next topic is the autocorrelation function. So what is an autocorrelation? What is the significance of using an autocorrelation function? We can see that the random process xt is a collection of different sample functions or different sample waveforms. Here yt is the different collection of different waveforms, or you can say time varying function, and here we can observe that xt is varying at a very slow rate, or it is fluctuating at a very slow rate, but here yt, this random process, is varying with very or fluctuating at a very high rate. So this fluctuation will give you some significant relation. So what is that relation? So that relation shows that we can find the autocorrelation. The autocorrelation of slow varying waveform will be wider, and the autocorrelation function for the highly fluctuating waveform will be very narrow. So the autocorrelation function for a slow varying waveform will be wide. Here we can see from this this autocorrelation function, and the waveform, that is yt, which is varying at a very fast rate, it is very narrow. So this classifies that whether our signal is varying at a very high rate or the signal is varying at a very slow rate. So this information we can get for the receiver in communication. So the autocorrelation function we have classified for slow and the rapidly varying signals. Now we will discuss what is autocorrelation and how to find the autocorrelation. So it leads to the spectral information of the random process. So we can get the spectral information of signals in communication. So correlation can be used to measure the similarity of the amplitude. So for different time instant t1 and t2, where we are relating the time instant, here we can see in this waveform that is t1 and t2 are the two different time instant, and we are analyzing the amplitude. So we are analyzing the amplitude at these 2 points t1 and t2, and we will see that in a slow varying waveform the values are not varying much, means the values are approximately same. But here in a fast moving signals or fast fluctuating signals, what is happening is the values are varying very rapidly at two different time instants. So this information will be useful for a signal which is delayed in communication. So that's why we are taking two different time samples, that is t1 and t2, and we are getting the amplitudes, and this t2 is nothing but the delayed version of the t1. That delay is t1 plus tau, or we can write it as t. Okay, so we are considering the random variables at the time instant t1 and t2 are denoted by x1 and x2 respectively. Then for a real random process, the autocorrelation function. Now this is very important. What is an autocorrelation function and how to define it mathematically? The autocorrelation function x for the time instant t1 and t2 is equals to the random variable x1 multiplied by x2 and hoar bar. It can be written as we have discussed earlier also, it is nothing but expectation of x1 or x2. So these are the different forms of notation. We can use any one, or we can write this as expectation of xt1 or xt2. So both are the same thing. We can use any of the notation. Either we can use expectation or we can use bar. So we do not have to confuse with that whether we have to use the bar or we have to use the expectation. Both are the same thing. You can find in different books that are written in different notations, so we can use any one. Now the power spectral density, which we'll be covering in our subsequent lecture. What is the power spectral density? So PSD stands for the power spectral density of xt is the Fourier transform of its autocorrelation function. So once we have solved the autocorrelation function for a random process, or we can say the waveform, then can find the power spectral density. So the autocorrelation function for different time instant t1 and t2, we are getting it as x1 multiplied by x2 bar, which is nothing but the integration from minus infinite to plus infinite. So here we have getting two variables x1 and x2, so it will be a double integral. That is the integration from minus infinite to infinite, integral minus infinite to infinite for the two variables, that is x1 x2 random variables, and the probability density function, this p of x, is a variable of x1 x2 at two different time instants t1 and t2, and we have the derivative will be dx1 and dx2 respectively. So hence we have the autocorrelation function t1 and t2 that can be derived from the joint PDF of x1 x2, which is the second order PDF. So this why we are saying it is second order PDF, because it is a function of two variables. Now what are the different properties of autocorrelation function? So there are three basic properties which you have to keep in mind. First property is the autocorrelation function which is delayed by the factor tau. So the delay factor is tau here. So we know that according to the formula of the autocorrelation function, it is the expectation of xt1 and multiply with xt2. So same here we are using expectation of xt minus tau into xt. So this will give you the autocorrelation function. So the delay here is minus tau. Now the second property is, if the delay is 0, if delay is the waveform is 0, then if we put 0 here, what we are getting? We are getting it as the expectation of x t minus 0 x and xt. So xt minus 0 will be simply xt, and what will get? Xt multiplied by xt. So what we can write it as expectation of x square t. So same here we are getting, if we are putting the delay is equals to 0, then we are getting the autocorrelation function rx0 will be expectation of x square t. Another property we can say that since it is an even function, so we can see here it is even function which is centered at 0. So at tau equals to 0 we are getting the maximum value, and it is an even function. So whatever we'll have at minus 1, the same value will have at plus 1. Similarly for different values of tau, we can see that it's an even function, so values will be exactly same. So value will not change if you are finding for plus 10, minus 10, or for any value. So this property holds good, that autocorrelation function is an even function, and we have rx tau is equals to rx of minus tau. The third important property is that if we have a delay in the waveform, or the autocorrelation function with the delay tau is the independent of the sign, it may be because we are taking the magnitude of the autocorrelation function, it is always less than the autocorrelation function at 0. And we can see in this waveform here, the autocorrelation function is maximum at tau is equals to 0, and it start decreasing in both the directions. So it for plus tau as well as for minus tau, it is decreasing function. So this property holds good for the autocorrelation function. So these are the three important properties of autocorrelation function. Now this is a property which is proved here, that third property we are proving, that expectation of xt plus tau plus minus xt whole square is greater than equals to 0. So we can expand it as a plus minus b whole square as a square plus minus 2ab plus b square. So after expansion, we have solved it as twice of expectation of x square t plus minus twice of rx tau, which is greater than equals to 0, and twice of rx tau, which is at autocorrelation function at 0, plus minus twice of rx tau. So we can equate the inequality, and we are getting minus of rx 0 is less than rx tau, which is less than rx 0. So this property is proved here, that is rx tau is always less than rx of 0. Now we'll classify the random process. So there are different random process we can classify in terms of the stationary, whether the random process is stationary in terms of time or not, or we can say it is time invariant or not. So according to that, we have the random process, where have the multiple random process. So in that, if we classify, if we find the function that the random process is having the expectation, or you can say the mean of the random process is constant, and if we find the autocorrelation function is depending on the time difference, then we will classify it as a wide sense stationary process. And if we are getting that the power spectral density is also time invariant, and even it is following the autocorrelation function is dependent on the difference of the time, and the mean is constant, then we will say that this function is a stationary function, or we can say it is strict sense stationary function. So there is wide sense stationary process, or weakly sense stationary process, or there is strict sense stationary random process. And the combination of all the three, that is, it's covering the random process, the wide sense stationary process, and the stationary process, is known as the ergodic process. So it is a combination of the strict sense and the wide sense stationary and the random process. Now we will see one by one what are these random processes. So what is the stationary process? A random process whose statistical characteristics do not change with time is classified as a stationary random process. So for a stationary process, we say that there is a shift of time origin. So what we are shifting? We are shifting the time origin, which will be impossible to detect. So in case of stationary process, if you are shifting the time, there will be not any change in that. So suppose we are taking this probability density function at a time instant xt1, and then we are shifting it by origin by t naught. So we are shifting this at t naught. Again, we determine the probability density function, that is px, that is xt1, the instant t1 in the new frame of the reference, and new frame will be t2, that is because of the shifting, t2 is nothing but t1 plus t naught in the old frame. So the stationary process, so we have to find the two important conditions for a strict sense stationary. Either we can call it as a stationary process, or we can call it as a strict sense stationary process. Okay, triple SP we can call strict sense stationary process. So for a strict sense stationary process, the PDF, if you are taking the two time instant t1 and t2, that is a combination, must be same. So whatever value we are getting at t1, the same PDF value will get at the time instant t2. So this means this is a strict sense stationary process, means the probability density function at two time instant is not changing, and it is saying it is must be identical for the stationary random process. So p of xt is independent of t. So even if you are shifting the time, if you are changing the time, there is no change in that. So the first order density of a stationary process, this is the first condition, that the probability density function is time invariant or independent of time. So the time function is lost here. Okay. So for the second condition, for a stationary random process, the autocorrelation function, so autocorrelation function at the two time instant, that is t1 and t2, must be dependent on the time instant t1 t2 only through the difference. So how it is depending? The difference, that is t2 minus t1. So this means that the autocorrelation function at 2 time instant t1 t2 is equals to the autocorrelation function of the time difference, that is t2 minus t1. So therefore we have the autocorrelation function, we can write it as xt plus tau. For 2 time instants the autocorrelation function, we have expectation of xt1 xt tau. We can write it as double integral x1 into the probability density function f of x t1 x t2 and x1 x2 and dx1 dx2. So due to the shifting in the origin, we are writing it as 0, and this is t2 minus t1. So this is nothing but the autocorrelation function t2 minus t1. Now for a stationary process, the joint PDF for x1 x2 must be depend on the difference in the time, that is t2 minus t1. Similarly the higher order PDF, so even it is applicable for the higher order PDF, that is the probability density function for all the variables x1 x2 up to xn, for the different time instant t1 t2 up to tn, that is the PDF of x1 x2 up to xn, t1 minus t, t2 minus t, tn minus t. And if we are shifting for the origin, so that is t1 minus t as 0 we are putting, so it is exactly same. So this is all about the stick sense stationary process. Now we will see the next one, that is a wide sense stationary process. So what is a wide sense stationary process? A process that is not stationary in the strict sense. So what is the meaning of that? That means we are following only two conditions. So two conditions we will check. The first is the mean, another is the autocorrelation function. So what is the mean? So mean should be constant. So mean expectation of x of t, or you can say x bar t, is constant. So the first condition is that mean should be constant. Second condition is that the autocorrelation function will be dependent on the time difference. So here we can see autocorrelation function at two different time instant t1 and t2 is equals to the autocorrelation function rx tau. Now there is one example based on the wide sense stationary process. First we will solve this example and then we will understand what is a wide sense stationary process. So I will read the numerical for you. We have to prove that the random process is given in this figure by the different waveforms. That is the ensemble of the random process, and this is given by x of t 1 2 3. It means I we can write, so values at 1 2 3 we have different waveforms, so 4 different waveforms we have. And here it is written that xt, this waveform, is given by the function a cos of omega ct plus theta, where this theta is an random variable uniformly distributed in the range of, so it is written that it is uniformly distribution. So according to the definition of uniform distribution, we know that for a particular range it is from 0 and it is constant for a particular range. And what is that range? Range is from 0 to 2 pi. So for 0 to 2 pi this uniform distribution will be constant. So this uniform distribution is in terms of theta, because theta is the random variable here, and we have to prove that it is a wide sense stationary process. So for that we have to prove two conditions. One is the mean should be constant, another is the autocorrelation function must be dependent on the time or the difference of the timing. Now let's prove one by one. So first is we have to find the uniform distribution. So first we are getting the uniform distribution. So we know that according to the uniform distribution it is constant from time interval 0 to 2 pi, and what is varying according to theta, and this distribution is given by p of theta. Now how we can find? We can use the identity of the probability that from minus infinite to plus infinite p of theta d theta, and the sum of the probability is equals to 1. So we know that the sum of the probability is equals to 1, but here we know that this function is uniformly distributed, means it is constant. So we can take this p theta outside, and we have from the limit 0 to 2 pi, so we are putting 0 to 2 pi, and we will integrate in terms of d theta. So we have simply theta, integration is theta, so limit, lower limit is 0, upper limit is 2 pi, that is equals to 1, or p theta is equals to upper limit minus lower limit, that is equals to 1, or p theta is equals to 1 upon 2 pi. So we have this density function. So we have already got the density function as 1 upon 2 pi. Now we can find the mean. So according to the definition of the mean, we can write it as mu, or we can write expectation of x of t. So according to this, we are substituting x of t. X of t is given by a cos of omega ct plus theta. So we are writing it as expectation of a cos of omega ct plus theta. So according to the expectation, we have from minus infinite to plus infinite, but our function is only from 0 to 2 pi. So instead of writing minus infinite to plus infinite, I am writing 0 to 2 pi, and we have x of t, p theta and d theta. So we are substituting the value of xt and p theta. P theta is equals to 1 upon 2 pi, which is also a constant value, so we can directly take it outside. It is 1 upon 2 pi. And what is xt? A cos of omega ct plus theta, but here this amplitude is also constant, so a is constant. What is left is integration from 0 to 2 pi cos of omega ct plus theta, and we are integrating with respect to d theta. So the integration will be from the range, that is 0 to 2 pi, this integration will be equals to 0. You can also prove it. The integration, cos integration will be sine. So sine for the limit omega ct, and integrating with respect to theta, so there is no constant here, so 0 to 2 pi, and sine 2 pi plus omega ct and omega ct plus 0, so both are the same. So upper limit minus lower limit, so we are getting sine of omega ct minus of sine of omega ct. So this will be cancelled out, and we are getting mean as 0. So here we have proved that the mean is a constant. Now next property we have to find, second property. This property we have to prove that it is dependent on the time. So I'll clean this slide first. I think this is clear to you. Then we will find the autocorrelation function. So what will be the autocorrelation function? The autocorrelation function will be given by Rx, t1 and t2 for two time instants. So we'll writing it as Rx at xt1 and xt2 respectively. So Rx for the two time instant, that is t1 and t2. Let's take the two time instant. So we can write it as the expectation of x of t1 and x of t2. Now we know that xt is given by substituting x1, a cos of omega c t1 for the first time sample plus theta and a cos of omega ct 2 plus theta for the second time instant. So this a is here constant, so we can take it outside, so it will become a square expectation of cos of omega ct 1 plus theta cos of omega ct 2 plus theta. Now we know that if we multiply it by 2 and divide it by 2, we'll get a trigonometric identity. So what is that? We have 2 cos A cos B. So we can write it as cos A plus B cos A minus B. So we are using the identity. So we have a square by 2 and cos A plus B we get cos of omega c T1 plus T2 plus 2 theta, and cos of A minus B will be, or we can write it as cos of omega c T2 minus T1, and theta will be cancelled out. So we will have these two terms. So we can expand it as a square by 2 expectation of this function, this first function. Now due to this, when we are putting the limit from 0 to 2 pi, this function will be equals to 0. Okay, and what is left with? We are left with this function. Okay, and what is that function? So if we are finding the expectation of the second function, because this function will be equals to 0, because here we have 2 theta, here we don't have any theta function, so it only we have a square by 2 cos of omega c T2 minus T1, and we have integration from 0 to 2 pi d theta, because it no theta is there. So if we integrate it, so previously we have a square by 2 cos of omega c t 2 minus T1. So integrating upper limit minus lower limit. So this 2 will be cancelled, and we can see that the autocorrelation function, which is given by simply the time difference. So it is a function of the time difference T2 minus T1. So this proves that this particular random process x of t is a autocorrelation function. Means it is wide sense stationary, and we have the expectation, that is a mean is constant, and autocorrelation function is dependent on the difference of the time. Now the next is the ergodic process. So the time average of the each sample function, for example, we can find the time average at x t, that is the time average limit t tends to infinity 1 by t integration from minus t by 2 to plus t by 2 x t dt. And similarly we can find the time autocorrelation function, that is r x tau, which is defined as the timing according autocorrelation function for the time. We are using the symbol to denote as the time averaging, because the autocorrelation function which we are finding earlier is the for the ensembles. So here we are finding for the time. So limit t tends to infinity, the time interval is from minus t by 2 to plus t by 2 x t t plus tau dt. So here this, when we are finding the time average, it is known as the timing averages. In there it is called as the ensemble average. So there is this difference between the ergodic and the autocorrelation function. So this is when we are following these two conditions, then it is known as the ergodic wide sense stationary process. So it means that the mean, the ensemble average is equals to the time average, and the autocorrelation function for the ensemble equals to the time autocorrelation function. So when we are following these two conditions 1 and 2, then we can say that this ergodic wide sense stationary process, the particular random process is the ergodic wide sense stationary process. So what we have discussed in this lecture, we have covered about the random process, that the random variable which is mapped with a function of time is known as the random process. Then we have discussed about the autocorrelation function and the 3 properties of the autocorrelation function. Then we have classified the random process in terms of strict sense stationary process, wide sense stationary process, and ergodic wide sense stationary process. So here we are going to stop our lecture. Thank you.